So this reading session is around these just two models basically, S4 and S6. But I'll also cover some SSM fundamentals, and also Yash will also talk about like what RNNs, why are they bad, and sort of that sort of stuff basically. So that's the goal, and
Okay.
so these are like this is the hype around SSMs. So I think if you see this, like the leftmost picture is like literally a mamba that's eating a drum somewhere, and there's a parallel as a like pathway where like Google DeepMind is also doing the research. So this the center animal is a griffin, and like griffin, mamba, and also birds are racing basically. So and yeah, um, and so basically this is the overview. So we'll talk about some history, like what problems are there with RNN transformers. Then I'll cover some SSM fundamentals, and then S4. Then S5 we've kept it for 11th October. Yash will cover that. Then I'll talk about Mamba, and we also have this event SSM, which is what we have been working on during the internship, and Yash will also cover that on 11th basically. And so again, if you see these slides, like some of the starting content has been taken from this DeepMind talk in UCL. I think that so that talk was based around like LRU and Griffin and like what DeepMind was up to, not about any of this stuff basically. So I think, and then so the preface is basically that like there's really a lot of math, and if you see the S4 paper, there's also a lot of like even Mamba. There's a lot of like out of the box programming, like some crazy CS fundamentals, and I personally think that like you should look at these papers from like extremely good thought experiments as well. Like they are obviously not whack at ML, but really like they actually deserve all the hype that's around them basically. And because I think we'll start with some history. I think Yash can speak on this.
Yeah, okay. So I'll start with the RNNs and LSNs mostly. So I think like most of us already know like all of these all of these models and architectures were proposed for time series data. So the most earliest models were RNNs, and the way RNNs work is was like in a very simple way. What it did was in an auto regressive fashion in the sense that it looked at a prefix of input, and using the prefix of input, it try to predict the next input. So let's say you look at the first 10 tokens or the first 10 time steps, and then you predict what is the output of the 11th time step or 12th time step, something like that. And they were very primitive in that sense. So if you can see something like here, so xt is your input at the current time step, and you maintain something called a hidden state. Hidden state is basically some sort of a compressed information of the inputs you have seen till now, and you'd want to maintain this because ideally, let's say you're talking about trying to predict some stock market prices, you're trying to do language model, something like that. What you would expect is whatever inputs you have seen till now in the past, using that you could predict the next whatever the next time step or the next price for the stock market or something like that. And ideally you want this to be compressed because storing it uncompressed doesn't scale well. So ht minus 1 is you could do some sort of a computation, some mlp or some non-linearity, and you compute this hidden state. And using this input and the hidden state from which you have compressed or generated from the seeing the previous times, is you generate the current hidden state. And using this hidden state, you can just pass a linear layer on this and generate the outputs. Now there are multiple variations of this. One of the main problems with using just this as is this is the naive architecture of an RNN. But the major problem, as you guys would already know, is like RNNs don't scale really well, even though they have this really fast inference of almost O of one for each times each prediction. But the problem that happens is like the gradient, the training is not very stable, it's not scalable, it's not stable because the gradients sometimes explode, they sometimes vanish. And that's and the changes which were made to propose changes which are proposed to fix this were mostly was adding more gating, changing the way you update this hidden state. Like here you're just directly using the previous hidden state and the current input, but that's sort of an aggressive thing, right, if you think about it. So if you add some more gating, if you add something more linearity or some other mlp or some other function which updates your hidden state, in that sense, that really helped with the gradients problems. But again, like the real problem was still like if it was able to capture the dependencies like on this time scale on a very large sequence length. They didn't really perform that well, even though they were computationally efficient. Yeah, next slide. Yeah, so again, now currently you wouldn't call this as history anymore, so history question mark. But transformers have really revolutionized the way we do any sort of sequence modeling, and I won't go much into the details about this because I think like most of us would know about this. But again, just like a quick refresher, the way you would do is like, yeah, Karan, could you go back to the previous slide? Yep, sorry. So the way you do is like you have a so what the basic motivation is that you want to focus you want whenever you're predicting the current output you want to have a focus from both the sides of your sequence, and that's how you generate it. So you would have something like a key query and a value matrix. You do some sort of a computation, and using those computations you see what might be the most relevant output. And there are various changes suggested to it, but again they really outperformed most of the RNNs and LSTMs because instead of the your traditional auto-regressive thing, they now looked at the whole sequence. Of course, you could enforce that auto-regressive by using certain masks and stuff. And so, yeah, basically that. Next slide. Yeah, this is the basic architecture again. Like it has an encoder which, like basically, like as you would guess, encodes the information about the input. And then if you're trying to do like a sequence to sequence translation task or sequence to sequence mapping, you need a decoder which would generate the relevant outputs according to for the corresponding to each time step. Then you could add mask, and it has other architecture details like that. So that's most part of it. But one main problem with the transformers, as Karan will also highlight later, and that's where really SSMs shine, is its computational time complexity. So when you're trying to generate the output for each token, when it's looking at the complete sequence, that is like an O of n computation. Now you're trying to do this for all the you're trying to do this for all your tokens. And since if you have, let's say you have n tokens and you have an O of n for each token, that becomes O of n squared. So that becomes really computationally expensive. And SSMs really shine into this because they make this as a linear time complexity. So and still achieving the same performance. So if this doesn't make sense much now, this will make more sense when we start explaining the details about how SSMs exactly work. Right, yeah, we can go ahead.
Okay, so yeah, that was just a brief history on like what RNNs and transformers are and like the problems with them, where like there's a clear research gap on like compressing the information and also doing it like efficiently, basically. So those are the two main areas where like this SSMs have come in, basically. So like compressing the information and doing it efficiently instead of so it's like you get to balance between both of them, basically. So before again we move forward, like there are two branches with SSMs which I just said. So one of them is like what DeepMind works on, and the other one is what these research groups work on, basically. So this happened starting with the LRU. So by the time like Mamba was released, there was a lot of theory thrown on in multiple papers by these groups at like Stanford and Princeton. And in order to disentangle that, they developed this completely newer form of RNN. So the whole goal of this LRE paper is to just match whatever S4 is doing, but do it in a completely deep learning way. So they start by creating a architecture that's very scalable, and then like try to parameterize it and try to like tweak stuff around it, which will make it very performant, basically. So that's why I call it. It's like very DL like, and in it also, and I mean tech, it is very performant as well, and it has good scaling laws and stuff like it's pretty good like it's almost equivalent to the transformer. But all these papers were like all the other papers like S4 S5 Mamba, they were made with like they were developed with a lot more mathematical intuition, basically. And like based like the original RNN paper. And yeah, I think that's about it for this slide. Then again, so as I said, like they fixed two important this is like on the left side you can see a brief history of like how papers have come out. So like it's been um, uh, Like I mean, starting with S4, it has really been very fast, and so I think Albert Gu is an author on all of these papers. So again, and apart from that, like they basically fix these two important problems with RNNs, which is, as you said, like stable training and scalable training. So we want to fix these two big problems basically. And so again, so these are the key ideas. You want to have a continuous time interpretation. You want to stick to some. So again, like these ideas might change as we see later architectures, but the main intuition behind S4 was basically this. Like they want, and this is how they created it basically. Like some specific initialization, and then the final concept is this discretization and diagonalization. So okay, so this is a continuous time interpretation of general state space model. So a state space model is like a concept from control theory or something. I don't know for sure, but sorry. So it's like a very general thing that describes a lot of phenomenon. Like so this xt can be any hidden thing, and then ut can be any output, and yt can be any output that you want to generate basically. So this is the original formulation, and this looks like rnn. It really looks like an rnn without the non-linearity, and but the difference is like it can be confusing on the surface, but current ssms do not use like no ssm basically uses this equation as is. Like they constrain the learning space basically, like what a b c and d can represent, by imposing very specific structures on these matrices that like actually work basically. And so I'll start with this initialization. So they derived this. The S4 paper has tried out a lot of initializations, and they have a lot of theory on why some of them work, why some of them don't work. But they derived that this specific matrix, which is they use some theory from echo networks. This works really well basically. So this initialization sort of helped the model get from 60% 98% on the MNIST task. So what my basic goal with this slide is that initialization was thought to be very important at the start basically, and they have shown that this initialization um, can provably capture long range dependencies basically. So they've proved it. So that's why it was again like it's like the Turing complete thing. So if you prove something, it obviously has a lot of merit. So um, uh, and these type of initializations have sort of stuck around. Like Mamba uses a different form of this, but they do have a specific initialization. And the other concept is this discretization and diagonalization. So again, our input is obviously not continuous time. Like so there are data sets that are continuous time, but most of the input that we like language modeling or say something like lidar data, maybe it's not really even continuous time, so it's a discrete system. And so what we would also want to do is like anyways, to work with this model we have to discretize it. So we discretize the model as in um, we basically make, instead of x prime, it becomes xk dependent on the previous time step. And so this now I think it'll look even more like RNN. And this is just one specific way to discretize the system. There are many ways to it, but this is just one of them. And delta is the like time step with which we are discretizing basically. So, and the final concept is this diagonalization. But really, like I mean, when I saw this, like why even diagonalize in the first place, right? I mean that's a very good question, but let's see how they actually do it basically. So what happens is like you can parameterize any matrix as a diagonal system, as an equivalent diagonal matrix basically, like using this diagonalization trait. And so what they do is like instead of working with this xk, which is a hidden variable basically, they work with this x tilde k. So again, it doesn't affect us because we never observe xk, so it's really no problem for us, but it really solves a lot of problem as we'll see. So now if you see, this d is clearly diagonal, and so like we'll discuss why diagonalization is important, but you can see that this d is now diagonal, and we have a diagonal ssm. So the again the S4 paper has proved why like why this is equivalent to any SSM that is not described by a diagonal matrix basically. So there's a proof for that. And for any arbitrary a bar, like this D can be complex. So with the freedom that D can be complex, like we can almost certainly diagonalize any randomly initialized matrix for sure. So does anyone have any questions up till this point, or like for this specifically? Uh, yeah, definitely typo in last question. So yeah, that should have been X minus. Okay, Ismail, then okay, then I'll move on. So basically, like all the two problems that we wanted to solve are sort of really solved by having it diagonal. So first, like why is this stable? So this is stable because like this D matrix that you know like is now diagonal, right? And when I like now when I refer to A bar, I really mean this D matrix. So because we say that A bar is diagonal, like now so any sort of differential equation from here, like we know that the blow up or like vanishing or whatever is really controlled by the coefficient of this recurrence basically. So A actually decides if the equation will blow up or like what will happen basically to it, right? So now what happens is when it's diagonal, we have access to its spectrum directly. Like the diagonal values are the eigenvalues, and so because they are the eigenvalues, like you can control the recurrence will blow up. Like suppose it's greater than one, it'll blow up basically, right? And if it's less than one, it sort of dies down. It's considered stable basically, right? So what you would do is like you would parameterize such that the eigenvalues are less than or equal to one basically. And then so there is a this very specific initialization that parameterization technically. So what you do is like you don't really learn the A matrix directly. You learn a phi matrix where the A bar is then parameterized as minus e to the power phi. So like if you see this, like this really isn't between 0 and 1, but like the way it's used in the paper, like A bar is again, if you see this diagonalization, um okay, again this diagonalization is not used in S4, but there is a specific diagonalization called zero order hold. So in that case what happens is like so A bar is also used in an exponent after discretization. Like A bar also becomes e to the power A bar basically. And in that case what will happen is this will ensure that it's between 0 and 1. Does that make sense? Or like I think that this is important, like you should know why it's stable basically. um, if anyone has any questions on this one. Okay. Okay, then I'll just move on. And then the other thing is like recurrence is linear, so there is no reason to worry about like exploding or vanishing gradients basically. Because of so what happened with RNNs is that the sigmoid inequality would actually cause a lot of problems. So now because this is a linear, there are no exploding or vanishing gradients. And finally, like why is it scalable? So it's scalable because of um, this parallelizable associative scan. So these associative scans, I think like talking about associative scans in general is like another whole research talk. And like it's a very like how it works out is like a algorithm thing, but there is a algorithm to actually do this computation efficient, like to compute this recurrence, like linear recurrence very fast. You can't do it if it's non-linear, but if it's a linear recurrence you can actually compute it extremely fast. So so that's one way to do it. And for the S4 paper, like if you just unroll this out, like this is how the input output for the calculated gates sequence will be, right? I think this should make sense like as is. So basically just like if you can pre-compute all of this, like you know all the matrices as is, you just have to do some computations to get these matrices, and then you can think of it like as a convolution. So it's literally this kernel, and so this star means convolution. So it's literally this kernel and the U is the input. So you can think of it as a 1D conv basically, a specific filter, not something. I mean something that is learned in a very specific way, right? So this like it's not like all the k parts of the filter are independent, but they depend on each other like in this very specific way, and that's what is different from a normal convolution. And um, so so the thing is like this scalable thing, you can do it even if A is not complex. So the thing A is not diagonal. So the only place where diagonalization helps here is like it reduces the flops. So instead of O of h square, you reduce the computation to O of h. That's the thing. And okay. And then I think most people will ask like why LRU, like if S4 has all these properties. Then like this is a slide from their talk. Then the LRU paper quite successfully like it challenges a lot of these assumptions like and a lot of the theory, and successfully proves that like much of the theory that I mean we haven't discussed is like unnecessarily complicated. And we'll move on to S4, but like if you want to see these slides, like listen to the talk, I think it's available online. And the LRU paper and stuff is also interesting in its own right. So I'll move on to S4, but does anyone have any doubts with the yeah, anyone have any doubts with the SSM fundamentals? So the thing is like if suppose it sort of works out because these fundamentals are like it's going to be reflected everywhere. So yeah. Um, okay. Then I'll just wait around for some time. Am I like is it better now or what? Like matlab can you guys hear? Okay. Okay, I think people don't have doubt, so I'll move on with this one. The second link is like for anyone. I think me, Yash, and Harsh have gone through this because of our internship. But this blog post is really it really makes your like. I mean, I understood all the math from this blog post and not the paper. So yeah. Okay. So now we'll start with S4. So this paper basically now it just unites all of these concepts into one thing and then makes it a learnable system. So they have this continuous time interpretation. They do have hippo initialization, but it's a slightly modified form. Then they use discretization. They have this convolutional interpretation. They use diagonalization. The I think the most important part and like what I was saying, like there are a lot of CS fundamentals is this extra stuff for like fast implementation. So like really fast implementation. It's not some and it's really not trivial to understand this or come up with this. It's not like it can't be scaled without this sort of like thinking basically. So I think that's really interesting. And as I said, like this paper also had a lot of like the initial proofs. So they proved that like it's a two-liner proof. They proved that like this diagonalization is an equivalence operation. So what this means is that say your underlying data is represented by some SSMX, right? Some which is characterized by these A, B, and C matrices. Then there is another SSM where A is diagonal, basically. Like and another SSM where A is diagonal exists, which is equivalent to your system. So they proved this. I mean, it's a small proof, but and then again, like why hippo because so as we'll see, like hippo is a matrix that can't be like it doesn't lie in the space of like diagonalizable matrices, so it can't be diagonalized, or at least it can't be stably diagonalized. So so we'll see this again, and the by what do I mean by stably diagonalized is that so if your state dimension, suppose like the hidden dimension that you're using, if it grows from like 2 to 3, then the values inside the diagonalized hippo matrix like they grow exponentially of like the state dimension increase. So what will happen is like if you actually want to learn something and you want like a non-trivial big state like say 128 dimensions, then the values inside the hippo matrix will be extremely big. So like you can't diagonalize it stably just as and then use it. So they also introduce like how to do it stably basically. Okay. I'll skip around this like these parts because we've already discussed like what is the continuous time interpretation, what is discretization and stuff. I mean all the concepts that I just picked up like these equations they are actually from the S4 paper. So we've already discussed all this. I think I'll just discuss this like how they parameterize the hypo matrix and what do they actually do to like reduce the computation basically like speed up the computation. Um, so first things like NPLR means normal plus low rank, and DPLR means diagonal plus low rank. So like why do we need these two matrices? So first like why normal? Because we want to do we want to perform conjugation, and by conjugation I mean we want to learn a diagonal system, right? So what happens is like if you so if you don't have a normal matrix, then um, like to learn so basically what they'll do is it becomes clear in the next slide, but instead of computing this kernel like as a multiplication like raising a k times and stuff, they do it in a different way, and it involves taking the inverse of a matrix, right? So now if a matrix has like a very high condition number, which is a separate concept, then the inverse is like very difficult to like the inverse has very high values and it like changes very quickly. And if it's a normal matrix, then the matrix has a condition number one, so like the values will be in the range of like what it was without inverting. So that's why we need normal matrices. And the second thing is why do we add these low rank stuff? So what we want to do is like we want to keep our matrices normal and normal and diagonal, and but there is going to be a small low rank part added to it. Low rank as in I think it might not be clear to Ashmit right now, but a low rank matrix is basically like this is okay. There's a definition of rank, and low rank matrices like again why they use this is because it's useful for them during their computation. So what's easy is basically inverting something plus low rank is a solved problem. So if you do something plus low rank, then it helps you out during computation. So that's why they add this low rank component, and they do it to so that they can approximate these hypo matrices well, basically. So because they want to do hypo initialization, and again that's why they actually initialize the hypo matrix. And the other problem is that even this would still not be enough, because powering up any matrix is like any matrix is just as complicated and if you do this exactly this naively, then this leads to about O of n square L computation just to compute the kernel, and then you again have to multiply it L times to actually get the output. So it becomes O of n square L square, which is very I think it's very uh, like computationally heavy, because now your computations are actually dependent on the hidden state, right? And for these models, like the hidden state is what actually decides this expressivity, right? I mean, if you have a bigger hidden state, you automatically have a better compression of the information. So like if you have say a two-dimensional hidden state versus a 128 dimensional hidden state, obviously the 128 dimensional hidden state is encoding a lot more information. So if you are square if you are if your complexity is of n squared in that dimension, then it's like a bad thing, right? So but they really do something crazy, and this they invent an algorithm that does this computation in O tilde of n plus L. So O tilde is basically log. So they introduce this algorithm that does it in log n plus log L space, which is log n plus log L time, which is something really crazy if you ask me. And so I think I'll move on to this. Is this clear? I think this is also very important. Like these two slides are extremely important from the S4 point of view. Mm, okay. Does anyone else have doubts? Otherwise, I'll move on. Right. Okay. So let's see. So this is an algo. I'll try to explain it as well as I can, but I still don't think like you can grasp all the maths or even I can grasp all the math. But I'll try to explain it as much as I can. So So the first thing is like instead of computing k directly, as I said, like we I think this might make sense to the electronics guys somewhat. We compute its spectrum because that's what we want by evaluating the truncated generating function. So I hope that makes sense. But so if you see the first line is actually computing the truncated generating function, right, up till the length L. So and this is why I was saying we need this inverse. So this star is basically because a bar can be complex. So this star is basically the inverse plus conjugation. So and um I mean this is just if you like informally this is like a GP with something like where the ratio is less than 1, you can actually get a sum like this. And so this is the same thing for matrices. And you can represent the generating function using this. And then the thing is like this generating function is like related to the matrix resolvent, and now involves this matrix inverse. So which is exactly why we needed those coefficient numbers of 1 and stuff like that. So this is where that normal thing comes in. And now the other thing is like and when you need the inverse, like this can be computed using, as I said, like again this, if you see the third line, like this is a famous identity called the Woodbury identity. Like this allows you, so if your matrix is something plus low rank, it actually allows you to compute the inverse very fast, if given that you know the inverse of the something part, right? So the low rank part it can actually approximate very well. So, and for us the something part is diagonal, so we already know the inverse like very well there. So that's why the third line makes sense. And to be honest, like this fourth line is extremely tough. Like it depends on using this Cauchy kernel, which I'm also not very familiar with. But this is used in many fast implementations. So if you assume that this can actually give you the coefficient, then coefficients of like these matrices, then this can allow you to compute the um, uh, like compute the kernel very quickly. So now so basically what you want is to like you want to take the inverse fast Fourier transform, and for that you need to evaluate the function at like at roots of unity. And so so the only question is like how do you compute something at the roots of unity without first computing it, right? I mean you need a closed form equation, otherwise how would you do it? So this is the whole thing. Like they do this whole thing to actually compute it very efficiently instead of actually like raising something to the power and then doing it, raising something to the power and then doing it basically. So I think I'll let you stare at this algorithm, and if you have some questions, which I think um okay. So okay. So by complexity you mean like the complexity of this algorithm? Or
Yeah,
okay. So I think me and Tejas also discussed this. So what happens is like computing it at the roots of unit takes L time, and then inverse fast Fourier transform again takes L log L time. So overall this takes like L plus L log L. So um,
yeah, but
this is
Vit is saying that it should take a long.
yeah. So basically what yeah. So the thing is I'm I'm still confused around like why if this takes like L log L time, then they do say that it takes O of like this tilde basically represents log. So they are saying that it takes log of n plus log of L time, but this inverse fast Fourier transform actually takes L log L instead of like log L. So um I think I'm missing something there, but I'm also not sure where it's going wrong. So I think if we see this, okay, wait, does anyone else have any other questions? Otherwise, yeah, I think I accept is just constant. So I think the second line is something I also accepted. But apart from that, I mean, you can also get an intuition for why the second line works if you read that blog. But I don't think I'm like I can explain it to you. Like there is a way how this can work out. So yeah. But apart from that, I think the third line and the first line, like First line is probably you've seen that in some math course, and this third line is it definitely will be taught to you in your FDS for sure. So this will follow along if you like have done FDS. At the end, I mean not a P. So, अरे भाई नहीं था. So we had it when bus up that I was teaching. And okay. And is it even clear with like how, I mean, if you know how the fast Fourier transform works, I mean, this should make sense. Like how this is the inverse fast Fourier transform and you can get the coordinate like this. I think they also have a discussion of this complexity. So let's also go through this once. So the key takeaway from this is like that it can actually do um, uh, like it has the time complexity of a and it has the time complexity of a convolution during training. So that's the thing, and it also has the optimal parameters. Like I mean, see, this is the parameter count maybe not very like like representative because what they have done is like they just say that this is the convolution size and stuff like that. They restrict it a lot. So I think, but what's important is that the training actually takes just so again tilde means log. So this is comparable to the convolution training time basically. And so again it can be parallelized as we just saw. Yeah. Um, if anyone can figure out how this works out in log L time, like I mean, I think I spent 3-4 days just wondering how this works out, but they do claim that it works out in log L time. Oh wait, okay, I think Tejas, I think it makes sense how. So basically, what they are saying is um, like just computing this filter can be done in I guess O of n plus L time in sequencing, if that makes sense. But again, like yeah, if you figure it out, do like yeah. So this is the architecture basically. So अरे भाई करण having breakdown by breakthrough नहीं. ठीक है. So this is the architecture like. So what you would do is like if you have h dimensional hidden state, you would replicate an S4 block h times. So the same block would be repeated h times. So that's why there is a cross h. And that's why this like if you see, so what happens is like you do this computation. So if you see O of n plus L times, so that is repeating in the, okay wait, I don't think you can see my cursor. So, yeah. So if you see this n plus L ka log is repeating here. So then why is there a b times h? So basically for each batch, for each hidden dimension, you have to do these many computations. So that's why it's b times h. And the same for this one. Basically. Okay. Okay. So this is one thing. And and so finally that was the complicated part. So now results. So if you see like it really like when this paper came out, like it was really phenomenal on this long range arena. And if you see like it's 20% increase on most of the other like above most of the other methods. And if you see like these path x, like there's no baseline that can even do solve the task. So I think that's if even on the average it's pretty good. So from what I remember, like pathx is a big like it's like you feed in images sequentially, and it has to classify them like pixel by pixel basically. So okay, okay. So okay, and so I did read Appendix D5. So if you are wondering, it doesn't have like it just has updated results from like future papers basically. And so again these are other metrics on like computational speed. So if you see this LSSL thing is actually a even more primitive to S4, but now no one uses LSSL because the S4 paper proved that LSSL is unstable. So that's there. And Both of them had the same author. If you can, I think you can guess that it was Albert Blue. Yeah. So, oh wait, oh, what is list ops? Okay. It's some data set again. I think it's a sequential data set, but I haven't. So I only looked at the toughest one, so that's why I just saw PathX and Pathfinder. Both of them are like feeded image wise, feeded sorry, pixel wise, feeded images, and you have to find out some paths or like some specific pixels which are actually good. So that's those are the two tasks. And so what I know is like pathx and these are very tough because like most big models will run out of memory because the sequence links are very big. And so that's why I only checked what these two data sets were because they were the most challenging. Like on this other data sets, I didn't really look into like what they actually represent. Yeah. Again, so I was at this so if you see like this is a like 5.35 times faster than 5.19 times faster than a transformer basically. um yeah. Okay. So before I move on, does anyone have any questions with S4 or anything about the algorithm? Okay, I think then we are good to move on with this one. So this is the S5 paper, and it'll be covered on 11th October. So yeah, so stay tuned for season 2, guys. And so now we'll move on to Mamba. And okay, yeah. So again, this paper is like this paper is sort of again like quite similar to LRU, but so it drops a lot of things that were considered very essential during when S4 was introduced. So like they drop complex analysis or dynamics, they drop hippo, and also like this is the main importance, like they drop linear time invariance. So this paper has three major contributions. So they drop this LTI thing. They like drop they create this hardware aware algorithm. Hardware aware as in again. So so as I was saying, like these papers have really a lot of like CS innovation as well. So like they invent their own CUDA kernels and stuff. And the other thing is like this model is sort of like only the second model in this whole space to actually scale stuff up to do language modeling. In fact, like there are multiple datasets that are not in the Hayana paper, and they were just done with S6. So scaling was a very big thing. Like this model was so popular because it had good scaling laws again. Like up till before this, like it was just a hype that it'll probably not be as good as Transformers, but this has actually a very good scaling laws. So like equal to a Transformer or better basically. And okay, so and so my main like the thing is like if you see algorithmically this paper is like a very small extension on top of S4, but the intuition and how they develop it is also very important, like the selection mechanism basically. And why do we call it S6? Because it's S4 models plus selection, and it's implemented as a scan. So those are the six S's. Okay. So again, so like I'll talk about the selection mechanism because it's important. So first thing is they say that um that people use the term gating, like they claim that people use the term gating in a very uh, okay, wait, okay, that's the next one. So first thing I'll cover is like why is selection important. So basically their intuition is they just hint it very slightly in their main paper. It's like it's very similar to LSTM gating, and you want to propagate information in an input dependent manner. So like the hidden state should sort of be able to select information selectively from the input. Like it shouldn't be affected by all inputs uniformly. So that's one thing which was not happening in the S4 paper. And what they even like they go one step beyond, and they say that They say that basically like selectivity is the goal of sequence modeling, right? And they introduce this effectiveness efficiency trade-off, which I'll talk about. So what they mean by this goal of sequential modeling is that so for example, take attention, right? It's both effective and inefficient because it does not compress context at all. Like all the context is just explicitly present, and this can be seen like from the fact that any sort of autoregressive inference requires explicitly storing the entire context, like the KV cache, basically, right? Which like directly it causes the O of n square thing, right? And on the other hand, like recurrent models are efficient because they have a finite state and implying constant time inference. However, like their effectiveness is limited by how well the state has compressed the context, right? So it depends. So what they're saying is like this: if you have a model that can select information perfectly, then that model is going to be efficient. So that model is going to be very important. So if that's the if anyone has any doubts with what I just said, yeah, you can ask now. Okay, yeah, I think I'll just explain this efficiency. Uh, Wait, am I audible now? Or okay, okay. Okay, so if I'm audible, so basically what I'll say is what I was saying is that there's a effectiveness efficiency trade-off. So like the effectiveness efficiency trade-off as in um so transformer models are effective because I mean we can see them working, but they are inefficient because they don't compress context at all. Like all the context is present as is, right? And that's why like all the tokens that a particular token can gain information from are always there. Like there is no storage of context basically, and so that's why they are inefficient. So because they don't drop anything at all. And on the other hand, like RNNs are very efficient because they just have one hidden state, but their effectiveness depends on how well that hidden state is actually representing the information. So what they are saying is if you want a efficient a sequence modeler, then you have to use something like an RNN. So you have to compress context. And so if you want an efficient plus an effective sequence modeler, what you have to do is have selectivity in some way. So that's why they say that it's the goal of sequence modeling, because if a sequence modeler has like perfect selectivity, then we can create an RNN and then we can have like we solve sequence modeling basically. So that's the main thing. Was that clear now, or like I mean basically does anyone have doubts? Okay, then I'll just move along with it. Um, and so I mean this is a very strong claim. Like if you see at it, like they say that this system basically cannot learn this induction heads task for like any a b c and delta. Like they haven't proved this, but that's what their claim means, right? If you don't have a selective system, like it can't learn this induction heads task. So this induction heads task is, I'll just briefly explain. So there are a lot of like color tokens or like some abcd basically, and there is a special marker token which is this black token. And so the task is to actually at the end of the sequence, wherever like or even in between of the sequence, wherever this token reappears, like you have to predict what the next token is, and it has to be the next what appeared in front of the marker before. So if this is like black and blue, and then it again has to be black and blue basically. So this is the induction heads task, and it really depends a lot on like if your sequence modeler can actually select information, because all these previous tokens are really useless. Like they shouldn't be in the hidden state at all. Like you don't need it for the task. So you only need information in your hidden state when you see a token, right? So what it's basically then again like what it's basically saying is that like if you have like you need some form of selectivity based on the input. So when you see this black token, you know that you want to store whatever comes next into your hidden state. And so yeah, that's the main thing. And okay. Okay. So this specific formulation, like once you've discussed it, like it's like how all research works. Like it looks trivial now, but like I also accepted it very trivially. But when I read the paper and the first appendix section, I think like this is very non-trivial and it takes a lot of time to actually come up with something like this and like actually motivate it. So I don't know if it's well written or anything, but I thought it was really non-trivial that they came up with this extension. Basically, like it's a very small extension, but I think it was very important. And so their formulation was actually they have provided a lot of discussion, like how they talked about it, like what discussions they had and how they came up with it. So like they discussed about hyper networks, gating, and data dependent transform, and recently a lot of like they also mentioned that this is not applicable to a lot of other fields basically. And but this is not GLU activation, and this is the other point I was saying. So GLU activation is just a gated linear unit. So a gated linear unit is you divide whatever input you have into two strings, pass both of them through different MLPs, and apply a sort of like a sigmoid on one of the branches, and you just multiply them both, right? So that's the gated linear unit. And what they basically meant was that like the term gating is used very lightly, and it really doesn't reflect like what the original LLVM gating really meant. And what they're saying is like their method is extremely based off of the actual gating basically. Like that's so they're saying like any other form of gating is not just random matrix multiplications, but um like you want your hidden state to actually reflect how the input is changing and stuff basically. So yeah. And does anyone have any questions with this? Okay. Oh yeah, probably Harsh. Yeah. I think yeah.
क्या क्या
No, no, kuch nahi. I'm just agreeing with what you just stated. So,
अच्छा अच्छा
uh,
agree 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 okay
yeah. Okay. So and they actually emphasize like that this gating is not a trivial gating basically. So again, this is so these are pre-results before we move on to like other parts of the paper. So this is just showing that like it can like solve the induction head task like perfectly. So tick means that it has like perfect generalization accuracy, so 100%. And so if you see like see transformers actually run out of memory, so you can't see how it performs on like very big sequences, but you can actually see that it sort of does even bad on like 2 to the power 14 basically. So and the other thing is like all models were only trained on sequence length of 2 to the 8, right? So nothing more than 256 length. And if you see like Mamba has perfect generalization accuracy up till 2 to the 20. So that's like a, a big order of magnitude above what it was trained and what it was seen, and it generalizes well. So basically what they're saying is that like selectivity is very important. And if you see this Hayana is a similar SSM paper, and it really can't do it because it doesn't have selectivity, right? So that's why they say that the selectivity is very important. And so this is they basically provided all intuition for why it's important. This is just showing that their model actually has perfect selectivity, like not perfect but like a very good selection mechanism. So yeah. um, okay, so this is the algorithm, and if you see this is the S for algorithm for comparison. And so if you see there's like it flows along the same way, but there's like just a small extension at both places. So what they do is like SB is just a linear layer on the input, SC is again just a linear layer on the input, and again S delta is just a linear layer on the input. So you do this and then you discretize it in a specific way. And so what happens here is like your B is now if you see the central dimension, like it has a L component, right? So it is actually time dependent, so this is not time invariant now, and this is a time varying basically. So C is time varying, delta is time varying, and stuff. uh, Wait, Aaron, okay, I think I explained that. Okay, so see. Okay, so yeah. And the other part is like why have they written like this recurrence and scan only? So because you have this varying time varying thing, you can't really do this thing anymore. Like you can't unroll it at once and then compute this kernel. So yeah, so you can't do a convolutional implementation basically. So that's why it's you can only do it as a recurrence. And I also think, like, I honestly think the hardware part is also very important. But this is all the intellectual contribution. Like these are all the ideas, and now it's just how they actually place it on hardware, which is also very interesting. But yeah, does anyone have any questions with this algorithm? Like how it's okay? Then I'll move on to this. So and I think they just like when I was reading the Mamba paper, what I saw is like they actually write that convolution is L times log L times something. So that's why I thought okay, like if the Mamba paper says that S4 has L log L complexity, that's what I was looking for. So that's why I didn't look more into it. So yeah, so if you see, this is basically it. And again, so basically what happens, like this algorithm is theoretically faster than even the S4 algorithm, like the S4 papers algorithm for small state dimensions, but it has a major problem basically. So I'll talk about that problem. But why is it faster than S4? So convolution in S4 takes BLD log L times, and Mamba conveys this BLDN time. I think you can work this out. It's actually not complicated. When I mean after I saw that this was L log L, this BLDN thing, like it literally, it's easy to see why this one makes sense. So wait, should I discuss this, or does it make sense why it's BLDN? So what happens is like okay, I'll just talk about it. So what happens is like for each batch and each hidden dimension, you have a n state SSM, and you have to do it for L time steps. So that's why it's BLDN. So I mean that's the easiest way to look at it. And and why is this faster than S4? So the other part is that the latter, like this MambaCon, has smaller constants, and so for n, if n is very less than log L, then this algorithm can theoretically be much faster than convolution. And the other part is like this is provably or visibly linear in the sequence length. So like theoretically linear in sequence length, not like a pseudo transformer or something. Like even S4 is say like L log L in linear length, sequence length, but this is like linear in sequence length. So yeah, and so the thing is like you actually want to utilize this speed up because you have a speed up, and so the only problem is that a naive implementation would materialize. So I'll talk about these terms, but I'll just say what they have exactly said. So they say that a naive implementation would materialize the hidden state of dimensions BLDN in GPU HBM. So HBM is the memory that is visible to the user, right? So like you can access anything in the HBM. So if you implement this as a for loop or anything, right? Then like you would always have access to this HT thing, right? You can always access it, and it has a dimension of BL. Like the whole hidden dimension has a shape of BLDN, and you would actually materialize it. So I mean, as long as the user can access it, there will be some memory copies, and there will be some like you will have to move around some memory. So what they say is like it's really not useful to a user to actually like you don't care how the hidden state is real, right? So what they do is like the default CUDA kernels would actually copy over and stuff, like they optimize it themselves, like the PyTorch CUDA thing. It will do it on its own, like it will try to optimize as much as it can, but it will copy over edge to the HBM, like for sure, because it's a variable in your code. Like that's the easiest way to understand it. So as long as it's a variable in your code, like it will be available to the user and it has to be copied to the HBM. So what they do is they write their own CUDA kernels such that they do a lot of they do the exactly same computation, but the edge is never visible to the user. Like the user just feeds in all the parameters for the computation, and the edge never comes out of the GPU SRAM. Like it never has, the user never has to see the edge to see the edge because the edge is never visible to the user. So what they do is like they write their own CUDA kernels such that they can actually copy over the edge. So what happens is like the user can access the edge, but the edge never comes out of the GPU SRAM. Like it never has, the user never has to see the edge to see the edge. So what they do is like they write their own CUDA kernels such that they can actually copy over the edge. So what happens is like the user can access the edge, but the edge never comes out of the GPU SRAM. Like it never has, the user never has to see the edge to see the edge. So what they do is like they write their own CUDA kernels such that they can actually copy over the edge. So what happens is like the user can access the edge, but the edge never comes out of the GPU SRAM. Like it never has, the user never has to see the edge to see the edge. So what they do is like they write their own CUDA kernels such that they can actually copy over the edge. So what happens is like the user can access the edge, but the edge never comes out of the GPU SRAM. Like it never has, the user never But that's what it means to do kernel fusion. Like they fused two or three operations into one big kernel, and they have implemented this kernel basically to not allow the user to see the edge and to keep it in the GPU SRAM instead of having memory writes, which is actually a bottleneck for this algorithm. Yeah, she didn't think so. Oh yeah, and as I said, like these seem like if you just read the paper, it seems very fancy, but like if so you see this video and stuff like it's easy to think of and not easy to implement at all. I would not say it's very easy to implement at all. So yeah, does anyone have any questions with why this is like, how this works? Okay, then I think yeah, this was again this is much simpler than the S4 algorithm. So yeah, and this is the actual thing. So if you see this HT minus one always stays in the GPU SRAM, like becoming visible to the user. So this like the user feeds in this HB like stuff in the GPU HBM, and then H always stays in the SRAM. It never comes out basically. So and that's why they have to write these computations basically. They have to exactly specify which tensor is supposed to be where in the memory. And okay, so again, so now we've talked about like the two ones like LTI drop and this hardware. So what about scaling? So as I said, like this is sort of the first paper in this branch that scales their model to a few billion parameters to test on language modeling and other real world tasks. And they got rejected from ICLR because at the time they did not have any LRA tasks. Like so, what happened is like there are a lot of SSM papers, and like I'm guessing this, and like if you see this is a big line, and so what would happen is like all these papers would emphasize that LRA is what works, LRA is what works, and um, to be fair, like they base their whole paper on selection, and they, I mean, frankly, it doesn't even matter if they have like LRA results or not. Like, I mean, obviously it's good to have it, but I think it's sort of understood that it'll work out well. But they got rejected because they had not reported anything on LRA when they submitted their paper. So LRA is this basically. This is the long range arena, like these all data sets. Okay. And yeah, this is like so now what happens like to scale it up, they stuck to this conventional transformer sort of thing. So if you see this is like you have a residual connection inside, a gated residual connection sort of. You have a convolution, you have the SSM, and yeah, that's basically about it. So, yeah. Um, yeah, yeah.
So the linear projections are the SASBSCs. Do they act as the SASBSCs?
The bottom ones, ये green वाले.
The green,
नहीं
yeah.
नहीं 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 नहीं.
Acha, acha, take it.
There is a different matrix for so that's all inside the SSM.
Inside
This
this, take it.
yeah, this
Hmm.
is not the SASB.
Hmm.
Okay. And this is an important theorem. So they show that the LSTM is sort of a special case of like Mamba. So like if you parameterize it very in a very specific way, like you can actually get the exact equation that describes the LSTM. So literally an LSTM. So, yeah. Um, okay. So now the thing is like their architecture is interesting as is, but there are like they also provide a very strong interpretation on like why it is interesting. So what they say is like they so this is the first thing like variable spacing or filtering context. So what this basically means is that if you have some input that's variably spaced and it gives some important information, then it doesn't matter like the what the spacing is between them, it will pick up that information. And filtering context means that it can filter out like useless parts about like useless stuff towards the task. Like if something is useless for the task, it can actually filter that out basically. So that's one thing. Then boundary resetting means like suppose you're using some sort of a language model and you feed in two PDFs, right? Like what will happen is like if you use a normal S4, like there will be some leakage of context between the two PDFs, even though they might not be related at all. And for a transformer, you can like cleverly modify the attention mask and get through. But if like what happens is like if you this can actually like this architecture can actually learn where this sort of like boundary is supposed to be basically. So this is the main, like the major takeaway is that this delta dictates a lot. And so if delta is tending to infinity, then it resets context and all the focus is on the input. And if delta tends to zero, then it's like the input is something regular, or it's the input is not very important, and so it just retains the context, and like there's massive focus on the context, so to say. And yeah, does anyone have questions? Because now it's just going to be results for this. Arey bhai. Okay. So again, so like they have pretty strong results. So this is that induction heads thing that we just saw like in this chart. If you see this, Mamba is like literally at 1.0. So like it's 100% on everything. So yeah, and these transformers are like these are different things like transformers, hyena, and there's a random baseline as well, which is where all of these things fall down to. And yeah, and this selective copying task again, like this is a different task that just so if your model is like perfect, is like very good at selectivity, like it will do amazingly well at selective copying as well. But I think I'm not going to talk about selective copying, like that's a different task again. So, yeah. And and then this is where it like actually like was good. So these are the scaling laws. So if you see, this purple one is the Mamba, and this orange one is transformer plus plus. So transformer plus plus is nothing, it's not a different transformer, it's just the transformer, a bigger transformer basically, nothing else. So transformer is their baseline with some same hidden state or something, and transformer plus plus is like a bigger hidden state, or like, so basically giving transformers an unfair advantage to for fair comparison basically. So even a transformer plus plus is like almost same as a scaling, like it's almost same on the scaling laws. And the same with here, like this is a bigger sequence length in fact. So if you can, yeah. I'll talk about scaling laws because they are actually very important, and people usually like don't know what these, like what do these scaling laws usually mean. So I'll talk about that. But these are like their results on language modeling. And and so interestingly, like a lot of the other things, like so they had, when they submitted their paper to ICLR, so they had only reported perplexity, like the perplexity on pile. And much of this is actually from their open review. Like I mean, they had already done this experiments in the rebuttal phase and they still got rejected. So like they computed this perplexity on this lambda data set, hella swag, they did all of this during the rebuttal phase. And they
एक सेकंड व्हाट फिर भी रिजेक्ट हो गए
yeah, so the reviewer said I'm like that it's like, I mean, you did a lot of, I mean, I haven't read that review perfectly, but like most of these results I've seen them in their open review. So if you go to their open review and see, like there will be a lot of
भाई
results on
पाइल
this.
पाइल पे रिजल्ट लाया वही इतनी बड़ी बात नहीं
no, so they had results on the pile from before, like that was everything they were reporting.
हाँ बट लाइक इन जनरल दिस इज नॉट इजी टू डू
Yeah. So
टाइम रन टाइम इसका रहेगा
okay,
कुछ 2 महीना
so before questions, I just want to talk about scaling laws again. So the thing with scaling laws is like ideally in an, like if you have a amazing sequence modeler, what should happen is like you increase the context, the performance should always improve, right? I mean, it should never decrease basically. So that's why the scaling laws actually show it. And the other part is like suppose at some point in the future, like we have infinite compute, like can we solve this task. So that's why these scaling laws are important. And um and the thing is, I'm saying this again because like people have not read that scaling laws paper, and that's actually like it's sort of like you have that gravitational constant in physics, right? So that OpenAI paper actually found those type of constants like 1.69 or something constants for a variety of multiple tasks, like say vision language modeling. It can never go below this perplexity. Like they found out that minimum perplexity that can be achieved with even
So
infinite compute.
like a Planck perplexity.
Yeah, exactly.
A
So it
Planck.
can't go
Oh
below
my
that.
god, bhai.
Yeah,
Crazy.
yeah, yeah.
Bhai.
And yeah, so the other part is like it only matters on language models how these scaling laws work out, because so the thing is like all of OpenAI's experiments, they didn't see a flattening out of the perplexity on language modeling. So like their experiments that they did, like it the perplexity would always go down as they improved compute. So I mean, so that's why it matters if it's actually going down on say like language modeling. If it was sort of like say flattening out, or like it was sort of like a L-shaped curve, then it would have been extremely bad for the architecture, because it would show that it like then transformers would be better basically. But this is actually good. This is a significant result basically. So finally, yeah. Any questions?
Infinite compute कहाँ से मिलता है?
uh, ask Google भाई.
चाहिए, थोड़ा चाहिए प्लीज.
Oh no. Uh, Also, this like Mamba has done a lot of experiments. Like there are experiments on DNA modeling and stuff. So I covered that. So like they do well on like DNA modeling, audio modeling and stuff like that. Yeah.
ऐसे ऐसा था तो पक्का पक्का अभी लाइक पोकेमोन बनाते रहते अभी.
um. Yeah. Does anyone have any questions? I'm gonna use Mamba for SOP. For real, bhai. If you can train a Mamba
देखा
from scratch.
यार अनदर नेक्स्ट इयर्स भाई. क्रेजी.
Oh no, yeah.
एक्सेंट थोड़ा सा लैकिंग है बट लाइक
भाई मैंने थोड़ा like I'm shocked कि सब लोग थे, like I mean only Ashmit left and I think he also had some legitimate
आई
reason.
थिंक सस्मित भी
मुझे
नहीं था
लगा था
ना.
सब छोड़ देंगे. Yeah, yeah, you can close the record.